Good morning.
Good morning.
Say, did you send out the homework yesterday?
Okay, I had problems. What I did was post it on Blackboard. Okay, I'll explain in a minute. Here, I'm admitting people. Yeah, it's on Blackboard.
Okay, thank you. I was kind of wondering if you had sent out or not.
You guys hear me?
What happened was I spent hours trying to send emails. And, oh, hi, Mr. Miller. And it refused to send them. And one from a student in my other class, it was actually blocked by her email. Okay, so everybody thinks I'm a crook. There we go. Okay, so yeah, I spent Thursday afternoon, today's Friday. Okay. Trying to do this, and then I finally just decided, well, I'll just put everything on Blackboard, all announcements, homework assignments, notes from class, and okay, every kind of document that I would have been sending to you on email, I'm going to post on Blackboard. Okay, so it's there for you, and it will be there for you. If I can just get things working here, it would make life so much simpler. But everything I try to do is hard. So, yeah, I'm posting everything on Blackboard. There is something on Blackboard now, and when you go to our class, there's this picture of this man. I don't have any idea who that guy is or how to change that picture or anything. But if you just scroll down, there are some announcements there now, or some items. Okay, so all these documents are going to be on Blackboard. Okay,
that picture is a placeholder.
Okay.
Well, because it's on another page that had nothing on its thing. It's the placeholder. The picture they use is a placeholder before the teachers put everything in.
Well, I don't know how to change that picture, and I don't like using Blackboard.
Okay.
Yeah, I don't like Blackboard. It's so unintuitive. It's so hard to use. But okay, it's easy to post things on it, and everything's going to be available to you. In fact, okay, yesterday I only had time to put up the notes from yesterday and your first homework assignment. But this weekend, I'm going to post everything I have sent out to you so far. So information about how to submit your homework, syllabus, and I forget what else I've done. Yeah, and the other notes from this week. Okay, I'm going to post it all on Blackboard.
I was going to ask you, Dr. Kennedy, if you received the links for the math shop from who's Anita Bryce. Okay.
No, I didn't. I did get a note that said everything's going to be online. Was it in there? Okay.
Well, I talked to some of the other kids who are tutoring, and they said, the links are on our schedule, and I guess she's going to send those out to the professors, and then the professors can send the links out to the students. Because again, I was on Blackboard, and I was trying to get into the math shop. I couldn't, remember the name of it yesterday, but it's called the math shop. That's where you go to get tutoring. But again, when I go on there, it's just listed as one of my courses. But if you're just a regular student, again, I also think Blackboard's a little unintuitive and clumsy, but yeah, so I couldn't figure out how to get there if you're just a regular student looking for it. You know, you can go on the main Lamar website and, you know, put it in the search engine, but then it's just like a web page that comes up. You can contact people there, but you know, there's no actual link to go in and just get a tutor. So
Right. So this
I
is
think
going
she's going to be sending those links out.
yeah, I will, if I get that information, I will post it on Blackboard. Okay. So you will have it. Yeah. And everything is going to be online. And if you want to meet with me, okay, I will set up a Zoom meeting so that you can essentially be in my office hours. But just request that and I will do it. And I'm going to try to set up Zoom meetings for my office hours, but that's going to take me some time because I'm going to have to enter all the people in both classes. Okay. Any other questions about things like that? Homework is posted on Blackboard. And from now on, everything will be posted on Blackboard. Okay. That way we can exchange information. But I want you to use those emails, special emails, to communicate with me. Okay. And to send your homework. When you hand in your homework, you'll submit it via email. And I will put instructions about that on Blackboard too, because I want it in PDF file. I talked about that before, but I will put information about it up on Blackboard. From Jake to everyone, next Friday. Lovely. Okay.
Someone had asked in the chat when the homework is due, so
It's
me and Jay could both reply to them, give them when it was due.
It says it on the homework if you pull it up. It's due next Friday, which is August 28th. Okay, due next Friday. Okay, let me see here. Okay, so pretty much everybody's here. That's great. Okay. Okay, so one more time for the people who came in late. I spent hours trying to create group emails, and then my email wouldn't send it. So I'm gonna post all assignments, all the class notes, all information, the syllabus, everything. I'm gonna post it on Blackboard. If you'll go to our class, there's a picture of this guy. I don't know who he is. I have nothing to do with that. But scroll down and there's going to be things posted so you can get them off of that. Okay. Are we ready to start class? Yeah. Happy Friday, everybody. I'm going to share the screen. I hope things get a little easier, but I'm not counting on it. Okay. Here we go. All right. Okay, here's our notes. All right. Well, I erased some of the stuff we talked about yesterday, but we're going to talk some more about limits. And also, I thought, I thought it was a very good question yesterday about continuity. And I thought I would say a little bit more about that. Okay, so definition. Definitions are really important in mathematics because you want to say exactly what something means. Exactly. Okay, so if we have a function from a subset of the reals and into the reals, and for us, this subset has to contain intervals, be made up of intervals. We say that function is continuous at the number a if, okay, a is an element of this set A. So the number A has to be a member of the domain of A for F to be continuous at A. The limit as x approaches A of f of x exists. Okay. And third thing, the limit as x approaches A of f of x is equal to f of A. F of A exists because x is in the domain, okay? So I know that f of A exists because of this, A is in A. So a function cannot be continuous at any number that is not in its domain. And we talked about the tangent function a little bit. And the tangent function, okay, its domain is all the real numbers except for odd multiples of pi over 2. So let me just go back up here. Let me just put this. The tangent of x is defined and continuous at each number x not in, okay, the sequence with two-sided sequence. Pi over 2, 3 pi over 2, 5 pi over 2, and that keeps going, but it goes in the negative direction too. Minus pi over 2, okay. Minus 3 pi over 2, I need to go back and let some people in. Yeah, the tangent of x is defined and continuous at each number that's not one of these numbers. So if the tangent of x is not continuous at pi over 2 because pi over 2 is not in its domain. But it is, okay, this is a true statement. It's not continuous at pi over 2. It's also true that it is continuous at each point at which it is defined. Okay, so I hope that clarifies things. Let me go back. Oh yeah, I need to admit some people. Just a minute here. So Marilyn and Daniel. Okay. Admit. Okay. And let's go back to the notes. All right. Okay, so any questions about that? Yeah, if a function's continuous on an interval, that means when you draw its graph, you're going to get this unbroken curve. Okay, so this continuity thing is really important. Okay. Yeah, and if you just say that f is continuous, You mean that it is continuous at each number in its domain. All right. And that was from yesterday. Okay, let's talk about the limit laws. These are, okay, actually, the definition of limit that we have so far is a little bit hard to use. I'm going to give you kind of the real definition later, but I don't want to load you down with too many things all at once. So these limit laws are actually quite easy to prove if you have a nice, rigorous definition. I don't think I've
Dr. Kennedy?
Professor, I think your screen went black.
It did?
Mm-hmm.
Yeah.
How'd it go black? Oh, wait a minute. What?
Yeah, are you screen sharing right now? Oh, there you go.
Yeah,
Okay.
better.
Okay. My screen went black.
Yes. Yeah.
Okay, now I'm not sharing the screen. Okay. But
You
when
are
I
right
was
now.
sharing, I'm okay. Okay. Let me
can
try
see
to
it
go
now.
back. Okay, try to go back to our math. Okay. And then tell me if it's still black, because if it is, I have no idea what's happening. I didn't see anything. I mean, I just saw my notes. Oh, by the way, yeah, I was having modem problems. The Spectrum guy came yesterday and he switched out my modem. So that problem should be solved. Oh,
Yeah, it's good now. We can see your screen.
okay. Can you see that?
Yeah.
Okay, good.
Yes, ma'am. I think the issue was that you were still screen sharing while you were in the Zoom application.
Oh. Oh. Okay. Okay, you guys have to help me out with this stuff. All right. Okay, so limit laws. These are pretty straightforward, not hard to prove if you have a good rigorous definition. But let's just accept them for now. They're plausible at least. So suppose C represents a constant. Let's see if I get my marker up here. So C is a constant. And we have two limits. The limit as x approaches a of f of x, and the limit as x approaches a of g of x. Both of those limits exist. Then, okay, if you take f of x plus g of x and take the limit as x approaches a of the sum of those two functions, that is the same thing as the sum of the limits. So you can break it into two limits and make maybe your problem simpler. Same's true for subtracting two functions. The limit as x approaches a of f of x minus g of x is equal to the limit as x approaches a minus the limit as x approaches, okay, left out f of x. The limit as x approaches a of f of x minus g of x is equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. And okay, if you multiply a function by a constant, so c times f of x, well, you can pull that c out of the limit. That's what number 3 says. The limit as x approaches a of c times f of x is equal to c times the limit as x approaches a of f of x. If you've got the product of two functions, you just take the product of the limits. So the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Same thing is true of a quotient of two functions. But with a quotient, you have to worry about the denominator being equal to 0. So this rule holds for quotients, provided that g of x the limit as x approaches a of g of x is not equal to 0. Okay, so that's 5 limit laws. And let's do a little, there are going to be some more here, but let's do a problem. And I think I want to go back to my pencil. Okay. So we're given that the limit as x approaches a of f of x is -3. The limit as x approaches a of g of x is 0. And the limit as x approaches a of h of x is 8. Don't know anything about f, g, and h or what a is. We just know what these limits are. But let's find some more limits from these. And if the limit does not exist, explain why not. Okay, so the limit as x approaches a of f of x plus g of plus h of x. Okay, well, we just had a rule that said that was equal to the limit as x approaches a of f of x plus the not okay. You don't know what integrals are yet. I'm not supposed to be talking about them anyway. So we've got the sum of two functions and the limit. We can break it into the sum of the limits. And the limit is x approaches a of f of x. That was -3. And the h of h1 was 8. So this is equal to -3 plus 8 is 5. Pretty straightforward. What about the limit as x approaches a of f of x squared? Well, that's really a product. F of x times f of x. And we just had a rule about that said that if I have a product of two functions, I'm taking the limit of that, then it's the same as the product of the limit. So this is equal to the limit as x approaches a of f of x times the limit as x approaches a of f of x. And that was equal to, and I forgot what the limit, what was -3, wasn't it? Yeah, it was -3. So both of these numbers are -3. So the limit is 9. Speak up if you got questions. What about 1 over f of x and that limit? Well, this is equal to, okay, it's a quotient.
The answer is it is okay as long as f of x is not equal to 0.
As long as the limit as x approaches a, yeah, f of x can't be 0. Wouldn't be defined at all, and the limit can't be 0 either. Okay.
Mm-hmm.
Yeah, we can't divide by 0. Okay, but this is a quotient of two functions, basically. This is limit as x approaches a of 1, which is a constant, over the limit, okay, x approaches a of f of x. Actually, if you have a constant and actually this is another rule, a constant it's a function too, okay? So if I have c equal to 1 here, well, I can graph that as a function. Don't want that. Don't want that. Don't want that. Okay. So if I take, I'll call it, H has already mean something. So let's see, what's the letter I haven't used? Let's call it K. K of X is equal to 1. Okay, that's a function. So I can think about this as being a function. And this function is just a horizontal line that goes through 1. And it kind of makes sense that no matter where A is, the limit as x approaches A of this function is 1, right? Because all the values are 1. And actually, that's a separate rule I'm going to go over in a minute. But, okay, so the limit as x approaches A of 1 is 1. And the limit as x approaches A of f, that was -3. So this limit is -1/3. What about f of x over g of x and that limit? Okay, that's a quotient. Now let's see. I forgot what the g of x limit was. It was 0. Oh, that's bad news. Okay, the f1 is -3, the g1 is 0, and the h1 is 8. Okay, let's see if I can keep that in my brain. Okay, well, we had a rule about quotients. This is true, but there was a condition on that, right? The condition was that bottom limit was not 0. So this limit, but it is 0. Ooh, I don't, okay. Well, okay, red works. But the limit as x approaches A of g of x is 0. So this limit does not exist. And okay, and this is something I've learned from my students actually. A lot of them just write D and E does not exist. Okay, so this one does not exist because that denominator function has a limit of 0. Okay, but what about G over F? Well, that would be, okay, again, it's the quotient of two functions. The limit as x approaches A of g of x over the limit as x approaches A of f of x. The f limit was -3. The g limit was 0. Now, 0 over something that's not equal to 0 is equal to 0, okay? And usually my students get confused on this, so let me just write something down here. 0 over 0 is meaningless. So it's not a number, okay? It's truly meaningless. If you take a number that's not 0, that's not a number either. You cannot divide by 0. And actually, kind of what's happening here, this is not as meaningless. This is not as meaningless as this is. This is kind of a limit of infinity situation where the denominator has numbers getting close to 0, which means that when you divide by a small number, you get a large number. but this is not a number, this is not a number, but 0 over a is a number as long as a is not 0. And that is equal to 0. Okay. And try to leave that there. All right, this is one more before we talk some more about this. I can use the rules that we already have to say that, okay, this problem, this is equal to, well, the limit as x approaches a of 2f of x over the limit as x approaches a of f of x, h of x minus f of x. And then by the rule about taking the constants out, the numerator becomes 2 times the limit as x approaches a of f of x. And the denominator, okay, I've got the difference of two functions, and I can just make that the difference of the limits by rule number 5, I think it was. And that's equal to, okay, the f limit was -3. The h limit was 8, wasn't it? Let me check. Don't trust my memory. Yeah, -3 and 8. Okay. If I were standing at a blackboard, I could just point. Okay. But I'm not standing at a blackboard. Or a whiteboard, more like it. Okay. Okay, but this is equal to -6 over 8 minus -3 is 8 plus 3, which is 11. Any questions so far? Are you all still there?
Yes, ma'am.
Yes.
Oh, okay, thank you. Okay, but so back to this idea of continuity. And in fact, this really comes into play with these limit laws too, but well, the limit laws hold regardless of whether you got limit continuity or not. But continuity is really nice because when you've got a continuous function at a number and you want to compute the limit, okay, all you got to do is plug in the function. And that's good to know and going to make life easier for us. Okay, but some more limit laws. If you take the limit as x approaches a of, okay, Mr. Miller? Of f of x to the n, then you can just take the nth power of the limit, okay? And we were just using this, but if you have c a constant, the limit as x approaches a of c is just c. Also, the limit as x approaches a of x is a. That kind of makes sense. You get close to a, the limit's a. And okay, it's also, well, this is kind of, oh, I wrote these backwards. That's what it is. I really should have put 10 first. If n's a positive integer and you take that's not supposed to be infinity. That's supposed to be a. Okay. Limit is And that's not supposed to be n. It's supposed to be x. The limit as x approaches a of x to the n is a to the n. And the same thing, so n's a positive integer here, and n's a positive integer in the rule above. For roots, though, you have to, if n is even, you have to make sure that a is greater than 0, because, for example, the square root of -2 does not exist. The cube root does, but the square root doesn't. Fourth root doesn't, and so forth. But yeah, you can just use both of those rules. And in fact, for n a positive integer, if you want the limit as x approaches a of the nth root of f of x, and the nth root of f of x exists, okay, so again, f of x would have to be positive if n is an even integer. But that's the same thing as the nth root of the limit. Okay, so now we have 11 limit laws. I have a sheet with all of these listed, and I will post that. Okay, and I also on that sheet, on the other side, I have a list of the algebra rules that we're going to need, because students sometimes don't remember them. Okay, but let's say evaluate some limits and justify each step using our limit laws. Okay, so we want the limit as x approaches 5 of 2x squared minus 3x plus 4. Okay, well, that's equal to, now I've got basically a sum of 3 functions. So I can break it up into the limit as x approaches 5 of 2x squared plus the limit as x approaches 5 of minus 3x plus the limit as x approaches 5 of 4. Now that's a constant. 4 is a constant. But the other two are functions. So I know that this limit's 4. This one, I can pull the minus 3 out and then use the rule about the limit as x approaches a of x. Okay. Pull the 2 out here. So let's do this one step at a time. Pull the 2 out. I had a rule number 2, I think it was, that said you can pull a constant out. And I can pull that minus 3 out for the same reason. And this one's just 4 because it's a limit of a constant. And we had a rule about that. Okay, so this is minus 2. All right, now I can evaluate the limit. This is x to the n, where n is equal to 2. This is equal to 5 squared then by this rule. Okay. And then we have minus 3 times 5. There's a dog outside my house. Yeah, that was a rule 2. So we just got these numbers, and now we have.
How did you get -2 at the beginning?
Oh, good question. Okay, thank you for pointing that out. Okay, yeah, please do point out my errors because I do make them. This is 50 minus 15 plus 4, and I don't like doing arithmetic, but okay, there's 39. Okay. Okay. And I was going to do this one, but what time is it? Oh, we've got time, I guess. All right. Oh, okay, just a minute. Come in. Hi. How are you? I'm fine. Hi, I'm teaching my class, actually. Okay. Okay, let me go back and let Mr. Miller in. All right. No, that's not that one. This one. Participants. Okay. And now stop do two. Yes. Okay. Yes, I agree with that. Okay. Now, any questions before I go back to the notes so far? Any questions? Okay. Okay.
Sorry about that. I got dropped.
Okay. Yeah, it happens. Yeah.
Looks
This
like we're
technology,
going to get some thunderstorms today here.
this technology is incredible, but it does kind of not work sometimes. Then you got problems.
Yeah.
Okay, this limit. And again, we can step by step. This is okay, it's a quotient of two functions, and as long as the bottom function doesn't have a limit of 0, we can just take the quotient of the limits. So it's the limit as x approaches minus 2 of x cubed plus 2x squared minus 1 over the limit. Now, why is it not writing? Okay. The limit as x approaches minus 2 of 5 minus 3x. And then, okay, we can break those limits down into, okay, let's see. Maybe I better go to another line. Okay, you've got basically got the sum of three things in the numerator there. So that's the limit as x approaches minus 2 of x cubed plus, and I'm going to go ahead and do two things at once. I can pull that 2 out because it's a constant. The limit as x approaches minus 2 of x squared, and then plus the limit as x approaches minus 2 of minus 1 over, can't forget the denominator, the limit as x approaches minus 2 of 5. And then I'm going to go ahead and bring that 3 out because it's a constant. Okay, so we can break it down like that. And now we can evaluate the limits.
I have a question real quick. Would the -1 in the numerator would it be a minus limit, or would it stay like that where it's just a
Oh,
negative?
you could write it either way.
Either way, it doesn't matter.
That's right. Yeah. In fact, I think of addition and subtraction as being the same thing because subtraction just means you multiplied the second function by -1. Okay. Yeah. Addition and subtraction go together, and multiplication and division go together. In my brain anyway. All right. So let's see. Let's evaluate these. We said that if you had x to the n, you could just take that -2, which is our a here, and write -2 cubed. So by that rule, this limit is -2 cubed. Okay. And this limit is 2 times -2 squared. And -1 is just a constant. So it's just -1. And the limit as x approaches -2 of 5. That's just the constant. That's 5. And then -3 times the limit as x approaches -2 of x, which is just -2. So we get -8 plus, okay, -2 squared is +4 times 2 is +8. And then the denominator is 5 plus 6. So we get -1/11. Okay, pretty straightforward. Any questions? Okay, so, well, that works nicely. And if so, all these, if you have a continuous function, you can apply these rules. At any number at which the limit exists. And as long as you have a continuous function, oh yeah, direct substitution problem, that's what I want. So if f is a polynomial or a rational function and a is in the domain of f, then to compute the limit as x approaches a, okay, yeah, look at that. Okay, all you gotta do is plug in a to the function, all right? And actually, that's true about polynomial. Oh, okay, what's a rational function? What's a polynomial? Okay. Maybe I should say something about that. Polynomial, and let's see. Make it allow me to do things. A polynomial is something like x squared plus 3x plus 4, or yeah, or x cubed plus 1. Those are polynomials. The general form is some number a sub n times x to the n plus another number a sub n minus 1 times x to the n plus 1. All the way down, you have a1x plus a0. That's a polynomial. And n is a positive integer. Okay. It's not a positive integer. It's not a polynomial. A rational function is the quotient of two polynomials. So if you have p of x and q of x, both being polynomials, then p of x over q of x is what you call a rational function. Yeah, so these are just terms. So, well, okay, polynomials, lines, the functions that give you lines are polynomials, the functions that give you parabolas are polynomials, so forth. If you take the quotient of two polynomials, you get a rational function. And of course, when you take the quotient of any two functions, you got to worry about where the bottom function is equal to 0, because when q of x is 0, the rational function there is not defined. So, yeah, polynomials and rationals are continuous on their domains, and that means you can use this direct substitution property on them, okay? But you can also use it on trig functions, as long as you stay in the domain, and exponentials and logs, which we're not going to talk about until later, and all kinds of combinations of those functions. They're all nice functions. So most of the functions you know about and are familiar with are continuous on their domains. And as long as a is in the domain of such a function, to evaluate the limit, all you have to do is plug the number a into that function. Okay. What about, oh, what time is it? Oh, I've got a few minutes. Okay, but you can't always use this direct substitution property. We want to evaluate the limit as h goes to 0 of 3 plus h squared minus 9 over h, I can't just plug in 0, right? Why not?
Because 0 is undefined.
Because yeah, because I can't divide by 0. Right. And thank you. I wish I could see you guys. Okay. I will adapt.
Just so you know, the reason my camera's off is because I'm getting some bad lag in terms of videos.
Okay, that's fine.
And I
You
hope
don't
turning
have
off my camera would help.
yeah, it does. In fact, my friend in I have a friend in Slovenia who's helping me out with the technology. We talk via FaceTime. Oh, he's so good with it. But he says he has his students turn off their videos whenever he's doing his lectures because it improved the quality of what they saw on their screens. Okay, so it's fine. I do like to see you all when you come to class and everything, but I can't see you all at once anyway because my screen will show a max of 9 pictures. So, and then if I try to move it over, it takes it forever to load. But okay, so find some way to do better. Yeah, but I do miss being able to see your faces. Yeah, typically when I'm teaching, and I look out to see if I see puzzlement on your faces, and I can't do that now. Okay, but you can't plug 0 into this one. Direct substitution probably doesn't work, but that doesn't mean there's not a limit. Okay, so what could we do? Well, we could try using some algebra here and change the form of that function in there. So the limit as h approaches 0, and then if I square that, the 3 plus h, that's 9 plus 6h plus h squared minus 9 over h. Well, the 9's add out, okay. And I've got the limit as h approaches 0 of 6h plus h squared over h, okay. Now, I've still got my 0 over 0 problem, but I can factor an h out of the numerator, all right? So more algebra. This is the limit as h approaches 0 of h times 6 plus h over h. And now, okay, remember when we're taking limits, we don't care what happens at a, and a is 0 here. I don't care what happens at 0. Okay, so as long as h is not 0, I can cancel those h's. And now I'm down to the limit as h approaches 0 of 6 plus h. And now I can use the limit laws to say that this was 6 because h goes to 0. Yeah, when I did this step right here, I got rid of my 0 over 0 problem. So the algebra helped me out. And okay, it's really important to remember that h can't be 0 when you're taking that limit, okay? H is close to 0, but it's not equal to it. And by doing that, I can evaluate the limit. So, well, this just says that direct substitution doesn't always work. Well, because some functions aren't defined at the number you're interested in. And if it doesn't work, it doesn't mean that you don't have a limit necessarily. You have to change the problem somehow to see if you have a limit or not and go from there. And I think I'm pretty much out of time. Yeah. Okay. So any questions before I leave the screen? Don't hear anybody. Okay. So let me go back to. Okay, any questions, guys? No? Okay, well, nice to see you. Okay. And I'm getting in class, okay?
You have a good weekend.
You too. You have a good weekend. We made it through one.
Bye.
Bye-bye.